and welcome back to the Cutting Edge stage. We have had an incredible day looking at technologies that we might be able to see in the next 5 to 10 years and how they'll impact our lives. I hope you're tweeting along with the hashtag CogX 2020 and that you'll enjoy this next session and store up your questions, because this one is about quantum computers. When you Google quantum computers, the first thing that comes up is, do they really exist? Which tickled me and made me realize that we must have a session at CogX talking about quantum computers, what they are today and what they could be in the future. So I'm really thrilled to introduce Nick Fishwick, who is going to talk us through those challenges with his illustrious panel. If you have access to the CogX app, you can stay afterwards to ask them questions. If not, ask your questions now in the app, and they will come to them later. Thank you so much. I will see you afterwards.
Thank you, Tabitha. My name is Nick Fishwick. As Tabitha just told everybody, my background is in national security and intelligence with the British government, and I retired a few years ago, and now one of my roles is as a non-executive director for a quantum computing company, CQC, and I'm very pleased that I've got 4 people in the panel today who really know about quantum computing. Order. So first of all, I have Anthony Annunziata. Anthony is director of the IBM Quantum Network, and what he's about is about creating a new ecosystem from scratch. That's Anthony's mission in life. Secondly, I'd like to introduce André König. André is the chairman of OneTech. He's an investor in quantum startups. So he's about building quantum brained initiatives right from the get-go and right the way through. Thirdly, I'd like to introduce Denise Ruffner. Denise is the chief business officer of Cambridge Quantum Computing. And finally, Tony Uttley, who is the president of Quantum Solutions, Honeywell. I'm delighted to have Tony with us as well. So I'm going to ask each of our participants a question, and they will answer the question, and we can take the discussion from there. And any questions that anybody wants to put from those who are following this discussion, please send them to me, and I'll try and feed them in if I can. So I started this session alphabetically. I'm going to continue it alphabetically. So it's a kind of a question for Anthony, which is about quantum. First of all, why is quantum important? Secondly, how do you get started in quantum? What do you need to get involved in quantum, to use quantum? And why is now the right time to do that?
Thanks, Nick. Let me take your first question. Why quantum computing? What does it offer? Quantum computing is really the first new approach to computing in decades, arguably even longer than that. Quantum computing at its core utilizes the laws of quantum mechanics, the revolution in science of the 20th century, to create the possibility of solving very hard problems. That is, solving problems that we have never been able to truly solve before. It doesn't matter how advanced our classical computing based on ones and zeros gets, it really can't solve certain classes of problems. And quantum promises to do so. That's why it's so exciting. Now, how do you get started is a very interesting question that has a much better answer today than even a few years ago. Because at the start of the session, as Tabitha reminded us, it's still a question in some people's minds about whether quantum computers even exist. I can definitively tell you they do exist, and you can start using one in about 30 seconds. Now that is a significant breakthrough, and that's only been true in the last about 4 years. So the first step to learning about quantum computing and getting started is to start to access the resources that have just come available in those last few years. Namely, being able to use real quantum systems online, on the cloud, and also a plethora of informational content, whether it comes in the form of YouTube videos, online tutorials, books, and other things. really a very easy way to get started now, and it really wasn't true even just a few years ago.
And on the question, why now, Anthony? Why would you say now is the time to look at this?
It's another good one. So think about quantum the way I started. Quantum can potentially solve problems that can't be solved any other way, really offering like breakthroughs in our ability to solve hard challenges in business and science and society. However, the flip side of that is that quantum is still pretty hard. Even though it's easy to get started, it's hard to master. It's hard to figure out whether you're an individual developer or an organization, how it fits into your day-to-day work, how it fits into your business strategy. So while it's extremely promising, it's also extremely challenging. So it's not too early to get started, even though the technology has a ways to go to come to full commercial fruition. The time to start now is now, because the potential is great, but the learning curve is a bit steep as well.
Cool. Okay, that's very interesting. Thanks. Well, I'm going to go on to a different question, and this time I'm going to turn to Tony Uttley. So I'm breaking alphabetical order, and I think Denise might have some views on this issue as well. So I'll probably bring Denise in after we've heard from Tony. I guess it's about timescales. Some people say quantum, it's always going to be ready in 10 years, and then 2 years later, it's still going to be ready in 10 years. And we've just heard from Anthony that actually, in some ways, it's ready now. So I guess I'd like to hear from Tony about timescales. Where are we in quantum, and where are we not?
That's a great question. So I've heard a phrase where quantum computing has been 10 years away for about the last 40 years. And the way we typically talk about it, or at least the way I talk about it, is in 3 eras. The first era is this emergent era. And it's an important one because it goes from quantum computers didn't exist and now they exist. So that is just a step change that allows people to be able to start actually operating on real quantum hardware. They can put in algorithms that get results. They can start to see what works, what doesn't work, and you can start to tune systems to continue to make progress. There's a third era, so you can tell I'm skipping one, and that third era is this classically impossible. It's this time where no matter if you use classical resources for the age of the universe, you could not solve the problem that you can solve with a quantum computer. And that still has a ways to go. There is there may be a decade to get to some of those really, really challenging things. But there's a middle era. And the middle era is what I call classically impractical, and others call it a quantum advantage. And it's where you can use co-processing of quantum resources alongside of classical resources to carve out problems where this piece of the problem can be done much more efficiently by using quantum resources. Just like you would do with a graphical processor unit, a GPU, you're going to have a QPU. And this era is starting right now. This is where we can look at problem sets that affect humankind and shrink those problems to the size quantum computers can deal with today, and then scale them rapidly as the capabilities of these quantum computers scale.
Great. Okay, that's very clear. And I'm going to ask Denise the same question. I guess you might answer it from a slightly different perspective.
Yeah, so thank you, Nick. At Cambridge Quantum Computing, we're a software company. So we work with existing quantum computers, both the IBM quantum computers and the Honeywell quantum computers, as well as others. And we develop software solutions for quantum computing. Right now, quantum computing is progressing actually at a very fast rate. And we're excited about the possibilities to solve real world problems, I would say, over the next year or two. What I did want to do is earlier, we have a question. Earlier, there was a question about how someone can get started on a quantum computer. And so I wanted to hand over to Anthony to talk about that for a second. But I just did want to say that quantum computing is here and everybody should be thinking about it now. And incorporating it into their overall company strategy. But Anthony, why don't you talk about how to get started?
Sure, it's kind of an easy answer, actually. You can simply go to ibm.com/quantum computing and start there if you'd like. We have been offering free access to quantum computers on the cloud for about 4 years now, and we've gotten hundreds of thousands of users and billions of executions on those systems, which has just been great to see, that level of growth. Now, I think others are starting to offer that as well. You know, I can defer to others on the panel if they have other ways to get started, but that's the one I know and love.
Okay, Tony, did you want to add a bit to that as well, coming from Honeywell?
Yeah, but I'll abstract it maybe a little bit, which is how do you get started if you're an individual, and how do you get started if you're in a company and you're thinking about this? It starts with education. Yeah, this is programming a quantum computer is very different from programming a classical computer, and unfortunately, instead of it being thousands or tens of thousands of developers out there, there are small hundreds of quantum algorithm developers out there. And so learning how you actually go do that is something that's important for individuals. And this is going to be important for a decade. So if you're out there thinking about what career do I want to have, thinking about doing, learning how to program quantum computers, learning quantum algorithm development, that's a pretty cool place to start. If you're a company, one of the things that I hear all the time is, okay, so you have quantum computers, you can do some of these early actions with them, but when is it going to solve my problem? And that's a great question, but it goes alongside how long does it take to insert a technology like this into your business infrastructure? There are a lot of companies, Honeywell is one of them, where the development cycle for your products might be anywhere from 18 months to 10 years if you're developing a new molecule. And in either of those timescales, you have to plan now if you're going to insert quantum computing into your processes. So sitting on the sidelines may say, well, I can wait till it really evolves and shapes itself. That may put you that length of time behind certainly all the forward-leaning companies and partners that I'm sure Anthony and his folks are talking to, as well as our team.
Great. Okay. Well, I think that's a good time to bring in André from the perspective of the same kind of issue, really. And I think a lot of people will be interested in this point of companies making use of quantum. And it's a question, the question is, are companies now pursuing quantum, André, as a strategic priority? And how should they be doing this?
They absolutely are. And my perspective, unlike my fellow panelists who build quantum hardware and software, is the one of a business executive, investor, and entrepreneur in this space. And companies are doing quantum today in many different forms and shapes. Anthony at IBM, Tony at Honeywell, and Denise, who is at the forefront on the software side of business development every day, all have clients and partners that use the current NISQ era machines, which are these machines that work today but still have some issues that we need to solve around them before they really can deliver results. Are available in the cloud, are available for certain other vendors on premise, and companies are working on them. They might not today get ultimate business results in terms of solving a specific use case just yet that they couldn't solve on a supercomputer or in another way, but they are getting what Tony and Honeywell calls this quantum practical, a real benefit in a learning curve and an experience in making fast progress along this implementation and execution part in quantum computing. There are also many other applications within quantum technologies, quantum information science, such as quantum key distribution, quantum sensing, quantum communications, that all have very real applications around encryption, security, the quantum internet, and many other things that are being deployed and developed today. There's a question from the public, Thomas, I believe, about a roadmap from these current NISQ era machines to, a real supreme quantum computer or a universal quantum computer. And IBM, Honeywell have well-guarded but very specific and detailed roadmaps to not only get from the machines that they have today to continuously iterate and improve them along a number of metrics. There are also vendors that are entirely focused on building these machines that might ultimately deliver thousands, if not millions, of qubits, this unitary computing measure of a quantum computer. So companies absolutely implementing things like quantum encryption, quantum sensing, quantum communication. They're really getting ready for the quantum computing era by learning and building and deploying and testing, and that's going to accelerate more and more.
And which sectors, André, would do you see the companies who are most active in investing in quantum? Which sectors are these? Finance, energy, where?
Yeah, we all have slides in our pitch decks of the different industries that will be affected first and affected most. Many talk about optimization problems, factorization problems, which you find in the traveling salesman problems, so logistics. How many trucks does FedEx put on the road, and what is the optimal route to deliver those packages in an optimal and most cost-efficient way? New compounds, new materials, and here we look at medicine. Obviously, in the context of the current COVID-19 pandemic, there was a question about quantum computer could help solve this and find a vaccine, which in theory it absolutely could. We're just not there yet, and there are a lot of other issues surrounding that. Finance is a big application to build financial portfolios, high-frequency trading, and anything that touches data in general, quantum computing for machine learning, artificial intelligence, and so forth.
Okay, that's really interesting. So I'd like now to throw questions to the panel. I'm going to victimize one individual to kick off with an answer to the question, but other people feel free to come in to add to it. The big question on everybody's mind at the moment, of course, is COVID-19 and how the world's dealing with the challenges that it faces. It's an open question, and André kind of touched on it in his last answer, but I guess I'd like to ask, I'll start with Tony. How is COVID-19 affecting the way that quantum could develop and should develop?
Yeah, I guess I would break that maybe into two parts. One is a little bit what André was talking about, which is the promise of quantum computing. So the promise of quantum computing absolutely has this ability to look at a natural model and disentangle it in a way that a classical computer cannot. And so being able to think about finding binding energies for a molecule and how that would affect kind of the human system, these are things that are on the horizon that you can tackle with this future quantum computer. So are we there today? We are not. What you can do is shrink down that problem size to a smaller molecule that you can test out. And the reason that's important is because we are going to cross a threshold, and even Google's announcement around quantum supremacy, it had a very particular point to it, which is you will cross this boundary where there's no way to fact check. There's no way to prove through a different classical method that was the right answer. And so taking this time to show that, yes, when you evolve these systems, you evolve the capability of a quantum computer, you are consistently getting that correct answer, is to some extent building up the trust that you're going to need for when you actually cross that boundary layer and you can start tackling development of new molecules or finding new ways to fight a disease like COVID-19.
How would you answer that, Anthony?
I think that Tony gave a good answer. Let me just maybe follow up on one or two things. I think COVID reminds us, I think, that there are many hard problems left in the world. problems where traditional computing, traditional approaches just have fallen short for a variety of reasons. So I think it provides one of those beacons of need for quantum computing. At the same time, it certainly does pose some practical challenges. Trying to empower a community, trying to engage a community, at the organizational level, at the individual level, it is harder. It is harder now, but I think that this is a temporary phase that'll pass.
Okay, Denise, any views on this?
Well, I'd like to talk about it from a different perspective, and that is one of a startup company or a lot of emerging quantum companies trying to do business in the midst of this crisis or pandemic. And it's, I think we all read in the newspaper that there's been a lot of difficulty in fundraising, but I'm really enthusiastic to see that there are still quite a number of quantum computing companies that are fundraising in this environment. I know at Cambridge Quantum, we've had tremendous business, and our business has not stalled at all due to the environment. So I would say that people notice that this technology really has legs and is keeping on moving. And so even though we're an emerging technology, I feel that the market and the industry understands that this is worth investing and worth moving forward even in this crisis time. André, I don't know if you want to add to that or...
Yeah, looking at the industry from the outside and analyzing, we have this famous term of the quantum winter that has been going around for a couple of years. At what point there might be a shakeout in the industry because of too much hype and results just not following suit. And this pandemic and crisis really has accelerated that. And I think, maybe surprisingly, a lot of companies have done tremendously well. Just yesterday, I spoke with the CEO of a Fortune 500 company that so far has looked at individual use cases in their quantum computing program that they have been trialing for a while now. His question was, is there a bigger picture? Is there something more core, more central to our activity, which is an industrial activity that we can be doing with quantum computing? And there's an increasing number of hardware, cloud, software, but also consulting, analysts, and media offerings and services out there to support all of this. So it is really progressing really fast. And Ryan in the audience asking if those systems will be robust or require future requirements. They are just developing extremely rapidly, notably thanks to IBM and Honeywell that really make this available in the cloud and allow everybody else to learn and to build, and that is fantastic.
Okay, that's great to hear. And are the levels of skills coming on stream as well? Young graduates, people with postgraduates in the areas that we need in quantum to really push this along. Are we seeing this increasing at a really exciting rate, or are any of you worried about it? Maybe Denise wants to answer it first.
Yeah, so let me take this. I'm really enthusiastic. There are an increasing number of programs teaching quantum even at the high school level, for example, through University of Harrisburg. There's a very robust meetup ecosystem. So there's a lot of education going on and a lot of interest in quantum. And there's more and more resources available every day. And this is in addition to, I'll hand it over to Anthony. I think that's my job right now, to hand things to Anthony to talk about what the Q Network is doing as around education.
Anthony.
Well, thank you, Denise. Yeah, let me talk just a bit about that. First, I'll say that, the long term, because of the initiatives that Denise mentioned and many other things, I'm very optimistic. I think that we will meet the talent challenge, the skills challenge on quantum. In the near term, there is definitely a skills challenge. Just finding people that can contribute into the various dimensions that are needed to develop quantum technologies is difficult at times. So to address that, through the IBM Q Network, we have a number of initiatives. We partner very closely with universities in a growing number to help develop curriculum that is a good match to what we think quantum technology development needs in the near future. We also have a very broad set of initiatives to produce open source and openly accessible content, including an open source textbook, video content, and many other pieces that can be used broadly, in universities, in industry, and other places. So we think it's very, very important. Obviously, we think there's a near-term challenge. Long-term, I think we'll be in very good shape because of a lot of the work that many people are doing, and I would count IBM as part of that.
Sure, good. And Tony, how are you finding the skills issue?
Yeah, I try to put myself into the shoes of maybe the person asking the question and saying, do I need to be a quantum physicist to have a job in quantum computing right now? It takes some of those, but what we have found, and I think what has made us successful, is you need to have a very multidisciplinary group of people who are focused on this. It takes quantum physicists, it takes quantum theorists, and then it takes electrical engineers and mechanical engineers and computer scientists, and it takes the folks that are helping us in our business development, and it takes our laws and contracts folks, because it really is a broad, exceptional kind of skill set that you need to be able to develop over time to make this scalable. And I mean scalable both in terms of getting bigger and more powerful quantum computers, but also so that the team itself is acting at scale. And what we found is that, yes, you may be a scientist where that's what you knew you were going to do for the last 10 years was quantum computing. But you also may be a software programmer that does Python coding that you kind of never heard about quantum computing until yesterday. And we have, and I say we, like the community, we have needs for both of those right away, because it's only with that kind of collaborative iteration that we've seen the success continue to rapidly mature.
Interesting. Do you have a perspective on this, André?
Tony works for Honeywell. I think everybody knows Honeywell because you have a thermostat on your wall that reads Honeywell. It's a very old and, I mean this in the best sense of the word, conservative company. So if you see somebody like Honeywell getting into this because they actually realize they have the expertise, but also the market to do this, that just shows you that quantum really is here today. As a user and a business, you might not see a financial bottom line impact or a new science fiction product or service just yet. But it is absolutely the time for anyone from starting at the high school level all the way up to professionals to start thinking about quantum. It's a different mindset. It's a little spooky, as Einstein called it. And it is something that is only going to accelerate and really touch every enterprise process that we as consumers interact with. And I think understanding this is really important to anyone, not just PhDs in quantum physics.
Sure. Okay, well, let's look forward to more of those skills coming on stream then, because it sounds like we need them. There's a separate question on my mind, which is about, which I hear people talk about a lot over the last few years, which is artificial intelligence, which could revolutionize the way people do business and also revolutionize the way people in government work. How can quantum be applied for artificial intelligence? Maybe I'll ask Anthony to kick off that answer.
Sure. I think the detailed, accurate response today is we don't fully know yet. What I will say is that in the last couple of years, using the devices we've been able to build, the near-term systems that we have seen interesting signs that quantum, relatively near-term quantum systems can accelerate certain aspects of AI, right, of machine learning training and of inference. That has taken some form in binary classification. There are no proof cases yet that this will definitively speed up or make more efficient or make more accurate this sort of classification, but some very encouraging signs in the last couple of years. Personally, I think that there's a great potential here. If you look at why a quantum computer works or why it offers the promise it does, the quantum device offers a space, essentially a number of variables that scale exponentially with the size of the system or the number of qubits. Now that, combined with the linear nature of quantum mechanics, right, the linear math behind it, actually makes what is the building, the basis, the potential building blocks of a very interesting way to perform linear math at exponential scale. So that actually is what you need to accelerate machine learning. The devil is certainly still in the details there, though. And so while we have work to do, I remain encouraged.
Okay, and Tony, are you encouraged as well so far?
Yes, absolutely. I think there are a number of areas that have the early stage showing impact, and that is things around big classes, things around optimization, things around machine learning, and chemistry or material science. And within that, again, you almost have to mentally rewind 50 years ago, something like that, 60 years ago, where somebody could compute on a piece of paper faster than the computer right next to them could compute. The tools that we have today, and it's right to think of them as tools, you have to go build up your skill set on. And what's going on is we are using quantum computers that are the capability that exists today on a problem that, as Anthony talked about, the problem itself scales, and it scales exponentially, which means that it lends itself much more to quantum computing than it would ever to classical computing. And you can take that problem and shrink it down and test it out on the systems that exist today, knowing that as you scale that up, you're going to have a larger and larger capability and therefore a larger impact. And so we're seeing that in artificial intelligence applications, in machine learning applications, in quantum chemistry applications, and it really is now both kind of getting the most out of that by let's call it tweaking the system, but also scaling up now the capacity of the quantum computers themselves to be able to tackle those larger problem sets.
And Denise, doesn't Cambridge Quantum Computing have a machine learning practice team?
So we do have a machine learning practice team. And I also wanted to mention that we recently have published some experiments that we've done on quantum NLP. So we're evolving where current NLP is around word recognition, and we're evolving to sentence recognition using quantum computers. And we've published our first set of results that were actually run on an IBM quantum computer. And there's a very exciting stream of research that we have a whole team working on, headed by Bob Cook from Oxford University, where we feel that we can make a huge impact in the future on NLP using quantum computing. So that's an exciting new development that we're all very happy about.
And what's your view on the issue of AI and quantum then, André?
I am very intrigued by it. I'm even more intrigued by this idea of data. So kind of a step before machine learning. And we live in a digital data-driven economy. A lot of our companies and businesses run on data infrastructures, data that you need to sort, search, ultimately analyze. So I think there's a future where ultimately quantum computing will allow companies in certain industries and verticals to fundamentally change how they work with their data.
If I could, there's a question from the audience from Edward.
Please.
Edward asked, with machine learning requiring more and more energy, so if you think about every time you double the size of a supercomputer, you're doubling the energy consumed. There's a lot of energy consumption there. So it certainly will be more green to use a quantum computer, which has much lower energy requirements for any computing solution, including machine learning. So as the technology grows, it certainly, at this point, looks like it's a much greener solution.
I would add, there's as I mentioned at the beginning, this era of classically impractical. when you think about what makes it classically impractical, there are typically 3 dimensions. First is it takes too long to do, so no one's going to wait for that answer. It costs too much to do, so no one's going to pay for that answer. But there's a third one, and it consumes so much power to do that you wouldn't do it. And you don't do it because your entire organization or your company is kind of centered around this idea of sustainability, and it just does not match up. And so absolutely, quantum computing has this promise of being able to do much, much more efficient calculations, again, for a certain class of problems that are these exponential hard problems. And we're certainly already seeing that has a lot of promise.
Sure. I mean, that might answer one of the questions which I had, which was, do you need quantum if you've got a supercomputer? Anthony, yeah.
I was going to just illustrate the point even further.
Sure.
So if you think about what it takes to double the capability of a high-performance computer, or any computer really that's based on ones and zeros, if you want to double its capability, essentially you need to double its size. You need to double how many bits you have. You need to double, how much data you can ship in and out of it. In a quantum computer, because of the exponential scaling that a number of us have alluded to here on this panel, you can actually double the capability of a quantum computer by adding just 1 qubit. So if you have 100 qubits, you want to double the capability. You can add 1 qubit to 101, and you get twice the size of the space that you can compute with. That is the power of an exponential. That's the promise of quantum computing. What does it take energy-wise to add 1 qubit when you've got a whole bunch already? Almost nothing. So the energy scaling is incredible, along with a number of other potential benefits. It's really a foundation-shifting type of technology in that sense.
Sure. Anybody want to add to that?
Well, my fellow panelists will
Yeah.
forgive me the analogy. I use an example between a bicycle and a jet plane sometimes when trying to explain this to a novel audience. You take your bicycle to go to the corner store in the morning and pick up your baguette, right? You wouldn't take a jet plane to go to that same corner store. Obviously, a jet plane is a lot faster than the bicycle. With the jet plane, you can also go to places where the bicycle, no matter how much you improve it, would ever be able to go. So supercomputers, classical computers, have been pushed tremendously, and we've done an amazing job at it. Classical computers, quantum computers are a lot faster, but that is not the point. It is different laws, different dynamics, a different thinking behind it that allows you to do things that classical computers, supercomputers just aren't good at.
And I think I want to just make the point that I think there's quantum computing and supercomputing are complementary technologies. I think we're still always going to need supercomputers, and we're always going to need quantum computers, but I don't think that quantum computers are going to replace supercomputers. I think I've seen some market research studies where they suggest that. And I think that there are problems that are better suited to a quantum computer, like what we've discussed today. And then that, if you're going to use a Word document or you're going to do something, you need a different type of computer. So I think that these are complementary technologies, not exclusionary technologies.
There's an interesting corollary to that, which is people ask me, so when is a quantum computer going to be small enough to be on my phone? And the answer is, it already is. That is how you can access the quantum computers that exist today, whether it's IBM's or Honeywell's. We've had our theorists literally from their phone sending in jobs to our quantum computers and getting results out. That is how the future of this is going to look, because massive data centers or how people access the internet today, you may not even know that there's a quantum computer that's running your job in the background. You don't care about that. You don't care about how that happened. You just care about the results. And that is very likely to be the way that most consumers and frankly most businesses are consuming quantum computing.
Sure. Okay. Fascinating. Well, we've just got 4 minutes to go. I just want to ask a question from a different perspective, which is about the difficulty of quantum. Why is it? Can you give an idea to the layperson why it's so difficult and why progress has been irregular? Who would like? Maybe Tony would like to start. I can see him nodding.
Yeah. I do. One of the things that I get all the time, especially when so there are different underlying foundational technologies to make different kinds of quantum computers, and Anthony will maybe touch on that for what IBM does. For Honeywell, we use something called trapped ion, which is using individual atoms to be able to turn them into our quantum bits, our qubits. And if you hold your hands together like this, you have about a trillion atoms in that space. Imagine having to sort that out and just grab individual ones and be able to physically move them, put them in a space where you can hit them with lasers, move them around again, hit them with more lasers, and all in an attempt to do one thing, which is to find out whether it's light or dark. That is the underlying technology, and it is hard. But I have to say one thing as a person who's leading this within Honeywell, which is I am really glad it is, because once you figure out how to do it, that provides a lot of intellectual property protection.
Anthony, do you want to add to that?
I guess I would just add by saying, quantum is hard for the same reasons that Einstein and Bohr and Heisenberg and the other prominent scientists of the 20th century thought it was hard. It's because it's different. It's a different way of thinking. We're used to thinking in concrete terms. We're used to thinking in computer science in terms of ones and zeros. That's been the paradigm for 70 years or more. Quantum changes all that. Quantum is thinking in terms of these esoteric concepts: superposition, entanglement, interference. These are not the way the world works. It's not the way we're used to thinking. If you can delve into that, though, conceptually, and in the mathematics behind it, then you can really uncover something that is truly groundbreaking and truly promising.
Sure, there's a few ifs there, but I'm encouraged by that.
Well, I can elaborate, but lots to say there, indeed.
Sure, André.
Yeah, and just by the way, there's a question from Diego in the audience for learning resources. IBM is a great starting place for that. Just Google IBM Quantum, IBM Q Network. And to what Tony and Anthony are saying, on the product and technology side, all of that is incredibly hard. The business side is also incredibly hard. What is a use case? How do you define it? What kind of team do you need around it? What kind of skills? What is your revenue model around it? I need to figure out the software. I'll call Denise. Denise has software, but it still needs a lot of work, even so it's the leading software out there. So there's a lot, even on the business side, that we just don't know yet. How does an investor do due diligence on a quantum tech startup? Just a lot of new questions that we need to find answers to.
Yeah. Do you want to comment on that, Denise? It's a good point.
Well, I think equally hard to the hardware development is developing effective software to solve real-world problems. And that's where Cambridge Quantum Computing specializes in taking the real-world problems and translating them quantumly, as we say, and developing a solution. So it's a very promising and very tough thing to do, but that's where we specialize.
Great. Okay. Well, I think we're almost out of time. Is anybody, I'm not seeing the questions from people who are watching this. Has anybody seen a question that they'd like to answer before we leave?
I think we're out of questions on time.
I think we're out, yeah.
Okay.
Tabitha.
So the good news is you'll be heading over to the Q&A room, which is where you'll see the questions that people have asked you.
I can't see the questions, Tabitha. Sorry, I don't know what I'm...
You're going to be transported like Spock into a new room, and that's where you'll see them. You won't even need to move. So what I'll actually do now, though, is I will close this stage, which is where we're streaming, obviously, live to YouTube. And those of you who are in the CogX app, you'll be able to head over to the Q&A breakout where you can ask that illustrious panel your questions. But for everybody else, good night. And
want access to more CogX videos? Subscribe now for free at cogx.co.